Right now, a spacecraft launched before most of your parents were born is hurtling through interstellar space, and somehow, impossibly, we are still talking to it. Voyager 1 is over 24 billion kilometers away, and the signal it sends back to Earth is so unimaginably faint that it makes a single snowflake landing on your hand feel like a sledgehammer blow. What you are about to learn will completely change how you think about human engineering and our fragile grip on the cosmos. To put that distance in terms your brain can actually hold, light itself takes over 22 hours to make the one-way trip from Voyager to us. Every command we send, every piece of data we receive, crosses a void that dwarfs anything our ancestors could have imagined. And yet the signal arrives, weak and trembling, but it arrives. This isn't luck or leftover momentum from a lucky launch window decades ago. Keeping that link alive is an act of relentless, almost obsessive human will, and the story of how it works is stranger than most science fiction. Voyager 1 was built in the mid-1970s using hardware that predates the personal computer by nearly a decade. Its onboard computer holds roughly 69 kilobytes of memory, less than a single low-resolution photograph on your phone. The spacecraft runs on 3 radioisotope thermoelectric generators, which convert heat from decaying plutonium-238 directly into electricity. There's no solar panel out there. Sunlight at that distance is essentially useless, too faint to power a light bulb. Those generators have been bleeding power at roughly 4 watts per year since launch, and the total output now sits dangerously close to the minimum needed to keep instruments alive. Engineers have been selectively shutting down heaters and sensors for years, just to stretch that shrinking power budget. The spacecraft's golden age tape recorder, its 1970s-era gyroscopes, its analog radio systems, all still running, all still responding. Something built before the internet, launched before most of its engineers were middle-aged, is still out there, still talking. Voyager 1 doesn't broadcast in every direction the way a light bulb throws light across a room. Its high-gain antenna focuses that signal into a tight, narrow beam aimed directly at Earth. Think of the difference between a floodlight and a laser. One scatters energy everywhere, and the other drives it into a single point. That dish is only 3.7 meters across, roughly the width of a large dining table, yet it punches a signal across interstellar space. The trick is concentration. The parabolic shape gathers outgoing radio waves and collares them into a beam just fractions of a degree wide. At 24 billion kilometers away, that beam has spread to roughly the width of Earth's orbit. But it still arrives. The transmitter powering all of this runs on about 23 watts, less than a refrigerator light bulb. What makes this work isn't raw power, it's precision, the kind that has to be calculated and maintained across decades of cold, silent drift. On the ground, NASA runs a system specifically built to catch signals that would otherwise vanish into nothing. It's called the Deep Space Network, and it operates 3 giant antenna complexes spread across the globe. One sits in the Mojave Desert in California, one outside Madrid in Spain, and one near Canberra in Australia. That spacing is deliberate. As the Earth rotates, at least one complex always has a clear line of sight to Voyager. The largest dishes in the network stretch 70 meters across, roughly the length of 2 Olympic swimming pools laid end to end. They don't just point at Voyager, they lock onto it with extraordinary mechanical precision, tracking a moving target billions of kilometers away. Even then, the signal arriving at those massive dishes carries less power than a single snowflake landing on your hand. The network has to amplify that whisper into something engineers can actually read and use. A signal from Voyager 1 arrives at Earth carrying less power than a single snowflake landing on your hand. By the time those whispers reach our antennas, cosmic radiation and the sheer distance have already done their damage. Engineers knew this problem was coming long before Voyager ever left the launch pad, so they built the answer directly into the spacecraft itself. Voyager encodes every piece of data using a mathematical system called a Reed-Solomon code, which wraps the real information inside a protective layer of redundant math. If bits get flipped or corrupted in transit, the code can detect the damage and reconstruct the original signal with remarkable, surgical precision. It's the same family of error correction logic that keeps your Blu-ray disc readable even when it's scratched. The fact that identical math protects both a movie night and a probe beyond our solar system is genuinely hard to process. That is the quiet genius hiding inside every transmission Voyager still sends home. Think about the last time you waited 2 days for a single reply to a single question. That is the reality of every command sent to Voyager 1 right now. Engineers at JPL type out an instruction, fire it into space, and then they wait. The signal leaves Earth traveling at the speed of light, and it still takes over 22 hours just to arrive. Then Voyager responds, and that answer crawls another 22 hours back across the dark. By the time controllers hear back, nearly 2 full days have passed on Earth. There's no back and forth, no quick correction, no, wait, we meant the other switch. Every command has to be right the first time, because a mistake won't surface until nearly 2 days after the damage is done. So engineers run exhaustive simulations, model every possible outcome, and only then commit a single instruction to the void. It's less like operating a spacecraft and more like writing a very careful letter to someone who lives impossibly far away. At NASA's Jet Propulsion Laboratory, a small team carries knowledge that exists almost nowhere else on Earth. These engineers learned Voyager systems from the people who built them, decades ago, in rooms that no longer exist. Some of them have spent their entire careers listening to a single spacecraft drifting further away every single day. When a command goes out, they won't see a response for over 44 hours, so every instruction has to be right the first time. They run simulations, cross-check decades-old documentation, and argue over margins that most engineers would consider impossibly thin. The youngest members of the team are absorbing knowledge that can't be Googled, can't be reconstructed, and can't be replaced once it's gone. There's something quietly extraordinary about people who measure urgency in light hours rather than minutes. This isn't just a job. It's an act of preservation, keeping a human-made object alive at the edge of everything we've ever reached. Sometime around 2025, Voyager's last power source will begin to fail, and the signal will fade. Engineers won't flip a switch. The spacecraft will simply grow too quiet to hear. That silence won't arrive all at once. It'll creep in, instrument by instrument, until nothing remains. The Deep Space Network will keep listening long after the last confirmed transmission, just in case. There's something almost unbearable about a dish pointed at empty sky, waiting for a voice that's already gone. Voyager itself will keep drifting outward for millions of years, long after every human who built it has turned to dust. It carries a golden record, music, greetings, the sound of wind and surf, addressed to no one we know. We sent it anyway, because that's the only honest answer to the scale of what's out there. The signal ends. The reach doesn't.